All right, welcome back to System Software. So we've concluded the introductory part of our course. We went over compilers in general. We learned about some actual system tools that hopefully you're getting a little more comfortable using if you haven't used them already. Being great at the command line will maybe it's a little bit of a steep learning curve or a shallow learning curve, I guess it really is. But it'll help you overall if you're going to do anything in computing. We went over these toy compilers. Today, the first one is due, and remember all you got to do is hand type out the compiler just to get you comfortable with the programming environment, make sure you have everything set up, and that's due tonight. If you have any questions about that, getting things running, you can ask the TA in the lab today. Next week, the generated parser and lexer version of the toy compiler we do. Again, that's just hand typing it out. Yes? I'm sorry, a second. Oh, sorry about that. So that's probably because I didn't put a submission. Thank you. All right, thank you for that. Okay, so today we're going to go into basically the real compiler that we're going to be building for this class, which you're going to be doing on your own without any help from, well, you can have help from others, but you cannot copy from others at this point. I'll be giving you ample amounts of template code. The trade-off there is you have to understand the template code to some degree, the API I've given you, but on the other hand, you don't have to write it from scratch. So it'll be less time overall. And over this next 4 lectures, we're going to be talking about the front end of the compiler that processes the input language, the words or tokens of the language, the grammatical structure, type checking. And then after that, we'll get into code generation, where we actually produce Intel x86 assembly. So before I move on, questions about toy compiler, questions about what we've learned so far. Yeah.
What date should we be able to start this?
Today. You should be able to start today. Yeah. So I've posted the project description and the assignment, the GitHub assignment. So you should be able to start today. And today we're going to talk about basically what you need for that assignment, and I'm going to basically start doing it with you in class. We'll do some live coding to show you what it looks like to do this project. Other questions? So for each of these projects, I've given you, I think, 3 weeks after each, about 3 weeks, 2 or 3 weeks, depending on the project, after each lecture that gives you the tools you need for that project. So the Simple C compiler will be due in 3 weeks from today. Type checking is 2 weeks. I guess that'll be a little easier. And then there'll be 2 sections for code generation, each about 2 or 3 weeks each. All right, so let's learn about syntax trees, the main data structure of the front end of the compiler. Okay, so we're going to review a little bit this notion of compilers, these parser generators. We're going to talk a little more rigorously, or at least a little more precisely, about what we mean by syntax, how you actually define syntax, how you define grammars. We'll take a break, and then we'll get into our actual compiler project, the grammar of Simple C. And I'll walk you through the tools you need in order to actually implement this first phase of the compiler. So as a quick review, if you remember, we had this we had this schematic of what a compiler writer sees when they develop their compiler. So they run their compiler through some compiler, and this generates the compiler binary. And this is the tool that we'll be writing in this class today, this project. And remember that it takes some source file in and produces an assembly file as its output. So unlike most of the programs that you've written, say for algorithms, where the input is some data structure or a number or some kind of data and you produce some summary answer of that, here the input of our program is going to be another program itself. And this, I believe, is really what makes writing compilers and thinking about this problem really hard. Because we're always tempted to think about what the meaning of the input program is, when in fact we have to think about all possible inputs of the program. And so the syntax we're going to talk about today is going to help us define all possible inputs of the program. And we also covered this bootstrapping problem. The bootstrapping problem is that, well, in order to actually write a compiler, if we're writing a C compiler, and we want to write it in C, well, we need a compiler already to compile it. So, anybody remember what the solution to the bootstrapping problem for compilers is? Or what you have to do if you don't have a compiler yet? Yeah. You have to write it in assembly. So you have to basically write this program directly. And then once you have your compiler, you can then write your compiler in the language that you're compiling. So any questions on this part? The input to our compiler that we're writing is another program, is this simple C program. And you got to keep that in mind when you're writing this, because it's got to be confusing. It's going to get real meta really quickly when you start having to actually implement this. We also looked at the phases of the compiler, the way we broke down our compiler. Remember in the first class I talked about the lazy way, the constructively lazy way to do programming is not to try to implement everything at once, but give yourself an easier problem to work on. Break down the specification, not the implementation, so that way your implementation is always correct for this really easy program. I always write a Hello World program when I start writing any new project. And so in the compiler's world, at least in the textbook definition of compiler, we have these well-defined phases of the compiler. We have the lexer, the parser, and in real-world compilers there'll be an optimization phase. But in our simple toy compiler we have these three phases: lexing, parsing, and code generation. And when you wrote that toy compiler, you wrote them in three separate C files, and we compiled them all together in GCC to produce our compiler, which I think I called toy. And this took in a program, although it was a very simple program. It took in a .toy file, and it gave you assembly code, or .s in the GCC world. And so this is how we broke down the problem of compilation. It's a complicated thing to read in a whole program and print out assembly code that's equivalent. And so compiler writers have broken down part of the specification for you already into these three or more phases. So questions about this, breaking down the compiler into these separate phases. And last week, in order to help make writing at least parts of the compiler easier, so lexing and parsing are well understood kind of classic problems in computing, to the point where we have tools that will write the C for us. So we don't actually have to write lexer.c. We can instead just specify the tokens in our language, specify these string patterns in our language, and generate the lexer. And for this class, we're using a classic tool called Flex. And same thing for the parser. Instead of writing this complex recursive C program, we can generate the C program that does the parsing for us, that does the processing of this syntax of the input program, and generate the parser for us. So today I'm going to be focusing on this part, the parsing part. So lexing is a really well understood classic problem. Once you take discrete, if you haven't already, you'll probably learn about regular expressions and finite automata, deterministic finite automata, non-deterministic finite automata. This is what's used to do the lexer generation, that theory. And so I've given you a lexer for this class already. So we're just going to look at this part today. How do we specify the syntax of our language? So one way to think about what Bison does is without something to generate the parser for us, we'd have to write this entire C program. A Bison file has C code embedded inside. It's like a complete C program with a main method or with a parse method. But inside, instead of writing C, you can specify, using this formal syntax, you can specify the grammar of your language, and then Bison will use that specification to generate C code for you. So I've given you a template of this file with the grammar specification of our language, and then your task will be, for this project, to fill in the code part of this grammar in order to actually build the syntax tree. Yeah?
Is the grammar in the separate language from C? Like, why is it offset in the back?
That's a good question. So C does not have a mechanism for specifying a grammar. It has if constructs, while constructs. You can implement a parser, but it doesn't have a language for specifying a grammar. So in some sense, Bison itself is also a compiler. That's why these are sometimes called compilers. So Bison has its own language and will process that language and generate code. It's not a general purpose programming language, but it is a code generator, just like any compiler. And so we'll go over today what the language for specifying languages is, language for specifying syntax is. So this is why I'm saying it's very meta. This is a meta language. It's a language that describes languages, and so it becomes confusing really quickly when you kind of try to talk about it in the abstract. But we'll see. I'll show you. I'll do in-class coding and show you what this looks like, and it's not so bad. It's just whenever you're using C, you're also using something like a meta language. You're not programming directly in assembly. You're using a language to describe computation, and then the compiler is translating that for you. Okay, and just as a quick refresher of what the lexer and parser do. So if we've got an input program like in our toy compiler, the lexer is the part that recognizes the ASCII input, which has no meaning to the machine. It's just numbers that don't have any computational meaning. And the lexer takes these raw ASCII encoded text and converts it into tokens. So it names these tokens for us. So that way, when we go to generate code, we know what kind of input was given to us, what kind of symbol in the language was given to us. And the parser is what generates this tree structure. It identifies which language constructs are being used. So in this language, we can't say 1:2, so something like this is invalid in our language, and it's the syntax that captures what the valid inputs in our language are. And what it also gives us is it gives us a data structure that represents which constructs are being used in the input language. So the parser is what says, hey, num op num is a valid part of the language, and it names them, and it says, I've seen a valid part of the language, and I'm going to get, and it's called an expression. And similarly, once we've seen an expression and a semicolon, if it was an expression followed by num, it would not be part of the language, and the grammar is what allows us to define what's valid in the language. And when the parser sees that when we've seen an expression followed by a semicolon, it can conclude that we've seen a statement, and it'll name it for you. And that naming scheme, this hierarchical naming scheme, is what allows us to more easily write a code generator. So does anyone remember how we generated code from this tree? What did we do to generate code? How did we use this tree structure in order to generate assembly code in the toy compiler? Yeah.
We burned the tree into Bison, I believe, right?
Well, this was after Bison, so this is what Bison helps us get. Bison helps us generate this tree. Yeah.
Can you read it infix?
So the parser is what does read this as infix. But how did we generate code from this? If we have this tree already, yeah. Yeah, so we traverse the tree, that is, we step through each node of the tree, and whenever we saw a particular construct like expression, what did our compiler do? What did our code generator do? So either you're working on it tonight, or you worked on it like 2 weeks ago and you forget. So all we did is whenever we saw one of these named constructs, we just literally ran printf and just spit out assembly code. That's all the code generator had to do. Once the parser named all of these constructs, and once it recorded the input language for us in this tree structure, all the code generator has to do is walk this tree one node at a time, and for each type of construct in the language, we just have a pre-made function that will just literally print out assembly code. And at the core of all of compiler really does is it takes an input language in some text file and prints out another text file in a different language. The tricky part is actually ascribing meaning to that language. And the parse tree is what helps us at least name the parts of the language. So if you were translating human language, you'd want to know when you have a sentence or a paragraph or a noun or a verb. All right, questions about this process so far? Okay, so having this data structure is very useful for the code generation process. And so there's been a lot of work over decades to do this input language processing. Yeah?
Is there a statement list about this thing?
Yeah, there would be, the toy, but there is a statement list about it. Yeah, so this isn't a complete toy program yet without a statement list. But decades of work have been done on processing the input language, taking a flat text file that has a sequence of ASCII code and interpreting the structure of it, naming the grammar constructs that the user has given you to the compiler. And having this, as we can see when you look at the code generator, having this structure allows us to very easily generate code because we just need one template of an assembly template for each one of these structures. And then we can just literally print out assembly code that corresponds to it. Now, actually designing that is a hard problem. Making sure it's correct is a hard problem. But in this class, I'll be giving you all the specifications, and then you'll be implementing this, and then you can see you have your own compiler that actually generates working assembly code that will run on the processor. All right, questions? Okay, so let's go through some terminology and formalize this notion of a grammar a little bit. All right, so in the grammar world, the name for the tokens, the actual words of the language, they're called terminals. And the way to remember this is that if you're traversing the tree, terminals are the tokens are the leaf nodes. So they terminate the traversal. They're the last step in the traversal in some sense. They terminate the tree construction. So kind of a synonym for leaves in some sense. And the inner nodes of the tree, the names of the constructs, are called non-terminals. So this is just the terminology used in the grammar world. And another way to think of the difference between these two is that the terminals are the actual symbols that the user gives you in your file. So this ASCII code, the names of these individual words that our lexer found, these are what the user actually gave you. They gave you a number, they gave you an operator, they gave you a semicolon. And the non-terminals, these are symbols in our language, but they're not expressed by the user. The user doesn't tell you, hey, I've given you a function here, or I've given you an if construct. Now, you may have designed the language to have keywords to help you figure out which structure it is. But the user's not telling you, hey, I've given you a program, I've given you an expression, I've given you... Instead, they just give you raw tokens in the input. And so the terminals, that's the part of the input that is actually expressed to you or uttered to you. Just like when you speak English or another language, there are sounds, there are phonemes, and nobody's telling you, hey, I'm about to tell you a sentence. I'm about to tell you a verb phrase. Instead, you infer the grammatical construct from what somebody told you. You don't have, actually, we do it pretty much automatically, so you don't have to think about the grammar construct. But you're likely doing some kind of grammar processing in your head. And so for the computer, to give the computer a way to name and represent these grammar constructs that are just implicit in the language, we use special symbols called non-terminals. They're just the names of the grammar construct. And in the compiler, in the actual machine that's running, these symbols are real. They're actually in a data structure. The name is a string or some data type, and it's physically recorded in the machine. So one way to think of what the parser is doing is the parser is taking this input text and inferring or figuring out what the grammatical structure of that text is. Just like elementary school students used to have to do, although I asked students that like nobody has to do this anymore. But in elementary school, they used to teach sentence diagramming. They used to teach you the grammatical structure of language. If you have to take a foreign language or you learn multiple languages, they'll teach you grammar, right? They'll say, if you take a Romance language, you conjugate the verb, and the verb has to match the subject. Well, those are grammar rules, and the parser is doing the same thing. It's figuring out what's the subject, what's the object, but for a programming language. All right, questions so far on these terms? So it's just terminology. Terminals are the leaves of the tree. Non-terminals are the inner nodes in some sense. Questions? Okay, so once we have the terminals and non-terminals defined in our language, so I've given you these. I've given you the terminals, so in the toy compiler they were numbers, operators, and semicolons, and I've given you the non-terminals in the toy compiler they were expression statements and statement lists. The grammar is just a set of rules that map symbols in the language, like expression or statement, to their parts. So let me give a concrete example in Simple C. So in the Simple C grammar I've given you, just like in C and most other languages, we've got a symbol for program that defines what the entire program looks like. And it maps to three other symbols. It maps to a list of declarations, a list of function definitions, and a main function. So in order to express this fact, this design of our language, we can make a rule that says program is list of declarations, list of function definitions, and a main function. So this is something that you kind of know in your head when you write code, but we need to embody this in a machine. And so we need to have something that's going to record in the machine these symbols that the language is using. And programming languages, at least today, are defined in this hierarchical structure, just like English languages or any human language is structured. You can say, guy goes to store, and I can modify this with clauses on the inside, like a guy goes very quickly and happily to the store. And nobody's confused about go and to the store. You don't think about that, right? You connect those two pieces in your head, even though there's lots and lots of words in between. And this hierarchical syntax that humans are already very good at innately, programming language designers have used for their languages as well. And so our grammar can capture this hierarchical nature of the language. And so here's an example in bold. So we had our original top-level definition of the language. It's a list of declarations followed by a list of functions followed by a main function. But we have this nested definition of what a list of declarations is. And it's a list of single declarations. And a declaration, just like in C, is a type name followed by a symbol name followed by a semicolon. And so syntax has this hierarchical nature, at least for human languages. And this has been used in designing programming languages. So here is what this looks like formally in Bison's grammar specification. So in the toy compiler, we had to write code. So to express this just in code that would actually recognize the input language, we had to write several dozen lines of code. To just capture the syntactic structure of the language, we can use this much simpler formal language for describing exactly what we talked about, describing the non-terminals of the language and how they're broken down, how they're composed into other symbols in the language. So to express exactly what we just said about what a simple C program is, we have on the left the name of our non-terminal. So this is the top of our tree. We have a whole program as soon as we've recognized a program. You think of colon as equals or is, or decomposes into. These symbols on the right. And on the right, in a production rule, there can be any number of symbols, both terminals and non-terminals. For defining a program in Simple C, there are only 3 components that we have for every Simple C program. They're a declaration list, which is a single symbol with this underscore, with a single symbol. A function list, which doesn't have the underscore for some reason. Maybe that's a typo. And a main function. And so these symbols capture all of the variety and nested structure of what a declaration list could be. It could be 100 declarations. It could be 1 declaration. It could be no declarations. Main could have any size of its body. And we can specify what a declaration list looks like by defining its symbol, by kind of recursively defining its symbol, just like our parser in the toy compiler was this recursive definition of the language. And so that way, when we go to define a program, we don't have to worry about every possible program. We can abstract away the grammatical constructs of the language and give them their own symbol, and then recursively define what those symbols look like in the input. So here's what the declaration looks like in Simple C. So the declaration is the type specification, followed by an identifier, and followed by a semicolon. Now here's where the meta-language versus the language can get really confusing. So this semicolon is the name of a symbol or a terminal, or a terminal or non-terminal in our input language. And the Bison specification language has its own symbols. So this semicolon here, this is ending the grammar specification. So even though it's like, why do you have semicolon followed by a semicolon? So this is the meta language versus the language. It's the same way if I say the word ball is a noun, the word noun itself is also a noun, but it's talking about the language. It's not what I'm uttering. Yeah?
So which one is the language and which one is the meta language?
So the whole grammar specification is the meta language. What the So what the Bison specification language allows you to do, it allows you to say any identifier followed by a colon, followed by any list of identifiers, followed by a semicolon. So that's Bison's meta language for defining syntax. This is where it gets very confusing, because we've got Bison has its own language, and then we specify the grammar in Bison's language, and that grammar specification is actually a definition of our input language. So don't worry too much about the compiler stuff. Just know that this is the syntax of a Bison grammar rule. It uses a colon to separate the production we're defining, and uses a semicolon to end the rule. And it's the symbol names on the left and right-hand side of this production rule. That's what we use. That's the meta language for describing our simple C input language. Kind of making sense a little bit? Questions? Yeah?
Do you mind going over why semicolon, semicolon?
Sure, yeah. So in order to define the grammar, we need a language to define the grammar. In Bison, we need a Bison language to define the grammar. So we need some rules about how do we say what the grammar rule is. This is where the whole meta thing comes in. And so that language, I can actually let me show the kind of So the Bison meta language looks something like this. It says you specify some non-terminal name and you follow it with a list of symbols and so on, and end it with a semicolon. So this is Bison's language for defining grammars. So this is the language for defining grammars. Just like you say noun, sentence, we need some way to express what the grammar structure is. So we're going to use Bison's language for describing languages in order to define what a declaration, what the pattern of a declaration looks like in Simple C. So in Simple C, this is what, this is Bison's grammar specification. Language. This is like the schema for defining, this is like the schema for a grammar production in Bison. And this is an actual Simple C program. So an actual Simple C program, if we want to express the fact that in a Simple C program, you have to put some type name. There are lots of different type names. You have to put some identifier. There are lots of different identifiers, but we want it to be one of those identifiers. And then you have to put a semicolon. So in order to express that definition of the language, we can use this Bison schema to express that. And the way we do that is we give a name to the declaration. We give it an actual name. It could be any name, but we give it a name. And then we say on the right-hand side what symbols that this declaration breaks down into. And so we can give a name to the set of possible type names. We can give a name to the set of possible identifiers. And we can give a name to the semicolon that must be part of the input. But Bison has its own language for defining these grammars, and it says you must put a semicolon at the end of the definition. Does that kind of make sense? Yeah, question?
So is the word semicolon already built into Bison?
No, it's not. So we defined it as part of our language. It's the lexer that defines it. So let me write this again so I can diagram this a little bit. So these symbols here, the actual semicolon and the actual colon, these are part of the Bison specification language. This is how you use Bison to specify a grammar. These symbols here are defined by the user of Bison. we make these up in order to name the different parts of the input language, our simple C input language. So these are names of simple C constructs. So the whole challenge comes in, how do we describe the fact that we want a semicolon in our input language? We need some symbols to be able to describe the language. So if you think in discrete or you go to take discrete, you'll see, and somebody actually asked about this last time, you'll see grammars written like this. Who's seen this in discrete? Okay, some. Yeah, so if you've seen this, okay, so you've seen this in discrete, right? So this is a grammar specification. This is like context-free grammars or Chomsky normal form. So this symbol here, this is not part of the language that we're processing, right? This is how you write the grammar. And so you can think of the semicolon as the same thing. So in Bison, you would just say these grammar rules like this. So ASCII doesn't have an arrow character. I mean, you could use a minus and a greater than sign. But these two ways of expressing this grammar are equivalent. So this is the grammar specification metalanguage. Whoops. Yeah, so these symbols are part of the grammar specification metalanguage, and the other symbols are the ones we create in order to describe the input language. Does that kind of make more sense? So these two ways of specifying the grammar are the same. It's just this is like what you learn in discrete. This is Chomsky normal form, and this is Bison's input language. Does that kind of make sense? More sense? So you can think of the arrow. I mean, this semicolon or this colon and semicolon is equivalent to just having arrow. It's the exact same thing. They're equivalent. It's just Bison uses, ASCII, and it has this, history of using semicolons to end things. Just, C has that as well. But yeah, good questions. Yeah, I really want to emphasize, you're dealing with kind of a tower of meta languages here. This is really what makes thinking about compilers hard, but it's also really useful in computing to be able to make this distinction. Yeah.
So for our first part of the project is probably writing in Bison.
You'll be writing in Bison, but I've given you the grammar already. So you'll have the grammar already, and then you'll be filling in code that will use the Bison grammar to generate the syntax tree. So Bison doesn't actually give you a tree. It just parses, it just recognizes the input for you. So in a technical sense, it's not actually a parser, it's a recognizer. It just allows you to specify the grammar, and then it actually will process the input and give you a call out so that you can have code that gets called every time it recognizes a grammar construct. And we're going to use that to create the AST. So I'll give you the grammar construct, the grammar specification, and then you'll be filling in code that will generate the syntax tree from that. All right, other questions about this? Yeah, this is definitely one of the more confusing parts because we're using a language, the Bison language, to define a language that's generating a part of our compiler, which is going to be, reading the actual input language and generating the output language. So I think when you go to write this and you see you actually go to use this and you see that it's really just describing, it's a pattern specification language for defining all possible input programs. I think you'll start to wrap your head around what this does, and then you'll see that when you give it different input languages, you'll get different parse trees, but you have a single specification of that grammar. That specification supports all possible simple C programs. All right, good questions. Other questions? Questions? Okay, so this is how in Bison we define the grammar in our language. Okay, I went over this already, basically, but the syntax tree is a record of how the input language matches the grammar specification. And so a syntax tree is for one, so the grammar is for all possible inputs to the program. A syntax tree is a record of why that program that you input satisfies the grammar. So these are the terminals of the language. These are the non-terminals of the language. So the terminals will end up as the leaves in the parse tree, and the non-terminals will end up as inner nodes, because the non-terminals always break down into other symbols. So the kind of key takeaway here, which I already kind of moved ahead at, is that the grammar is just a way to specify all possible inputs to your program, all possible syntax trees. So just like in C, you can't say x, y plus minus. You can't say that in C. It has no meaning. The grammar is what provides those specifications of all the valid orderings of symbols in your language. The lecture just finds what symbols there are. The grammar says, here's all the possible orderings in the language. And so this comes a bit from, or this comes kind of directly from, I think I showed this before, but this comes directly from this notion of syntax as a distinct part of language processing from Noam Chomsky's work on computational linguistics. And it's this idea that it's not enough to define a language by its dictionary, by just a set of words. There are restrictions on the orderings of words. So even in English, for instance, you might say big red car, but few people say red big car. It kind of sounds weird, right, to say red big car in English, even though you can probably infer the same meaning. And so this sentence, colorless green ideas sleep furiously, is used to illustrate that even though these are all words that we all recognize in English, the ordering of words has some, we recognize some restricted orderings of the words. So this furiously sleep ideas green colorless, this sounds like gibberish, whereas the first one, even though it's hard to ascribe some meaning to it, feels right? Colorless green ideas sleep furiously. It has a clear subject, verb, object structure to it. And it's this grammar specification that allows us to define what these valid orderings of the input are. So you can think of, yeah.
Are parse trees synonymous with syntax trees?
Or say again?
Are parse trees and syntax trees the same?
Yeah, well, I'm going to use them the same way. So the parse tree and the syntax tree or concrete syntax tree. We'll talk about a different variety of this tree called an abstract syntax tree in a little bit in this class. But yeah, you can think of it as the same. So if text files can be any sequence of ASCII characters, or say binary files can be any sequence of bits, text files can be any sequence of ASCII characters, the lexer defines restricted sequences of tokens. And then it's the grammar that says which order these tokens must be in to be a valid part of the language. Okay, and then like capturing this sentence, noun, verb structure, the theory is that Chomsky had, which may not be, I'm not sure how much it's held in linguistics, but the theory was that this grammar structure, this kind of symbols for non-terminals, was like physically embodied in your brain. This was his theory as to why humans process language the way they do. For instance, when children learn language, if they don't know regular verbs well, so they might say, I hurted my knee. And you may say, well, that's wrong, because you're supposed to say, hurt my knee. But grammatically, it kind of makes sense, because if you have this pattern of putting ed at the end of every word to make a past tense, then actually it's a kind of cleaner grammar. It's a simpler grammar. So this was his evidence for, part of his evidence, that grammar is somehow actually physically built into the brain. And this work on computational linguistics kind of led to programming language processing, because you had this computational theory about how language is processed, and this is actually what we're doing in the machine. We're implementing that computational linguistics in our parser so that the machine can actually process the parts of the language with real symbols, with physical symbols. We're physically embodying the grammar of the language in the machine. Okay, So practically, for the compiler, this allows us to define all possible inputs to the program. So unlike, say a sorting algorithm, it's always going to be an array. The possible inputs to a program are all valid programming languages. It's a huge set of them. The grammars allow us to specify what all these possible inputs are. Okay. So the way these constructs work, so if you've taken discrete and you've learned about Chomsky normal form, just having production rules isn't quite enough. So if we just had one way to say a sentence, well, we wouldn't support all the various ways to say a sentence. Or if we just had one kind of declaration, we may not support, say, struct declarations or other kinds of declarations. So the way these grammars work is the same construct name can have multiple rules that it matches. So for instance, the type in a declaration isn't always the same type. There are multiple types in our language. So in Simple C, for instance, we have int and char. And the way we express that in a grammar is just by writing two rules for the same construct. We just say a type can be an int or a type can be a char. So Bison supports this syntax as part of its meta language, so colon, pipe, and semicolon are part of Bison's language. We can say this same thing, what we said here, where there are true productions that match type. We can just express that like this in Bison. There's syntactic sugar for doing this. So another way to think of this is we're kind of like saying or. We're saying a type either matches the int keyword or it matches the char keyword. That's a kind of informal way of thinking about what this means. And so it's up to the parser to be able to figure out which version of type is seen in the input, and that's what the parser generator does for you. Questions on this? Yeah?
Well, if you want to upgrade type, could you just
Yeah.
make a line then?
You just do another pipe? Yeah, that's exactly right. Yeah, another line. Yeah, but we'll see that when we look at the actual Simple C grammars, that a statement can be while, can be if, can be assignment. And so this is how you express the various alternatives there are for what a statement matches to. Yeah?
Can you write it horizontally as well?
Yeah, you can write horizontally. So just like in C, line breaks and spacing are removed. But that's specific to Bison. In the Chomsky normal form, this would, you don't have this in the kind of classic Chomsky normal form. You'd have to just say, A goes to B, A goes to C. Yeah, something like that. So if in discrete you've seen this, you might have seen this in discrete where they have multiple productions for the same non-terminal. Okay, so I hinted at this a little bit last time, but another way that the input is potentially infinite is that you can have any number of declarations in your language, any number of statements. You're not restricted to some finite amount. But our grammar specification, we want it to be finite. We don't want to have to write down every possible input, every possible infinite input. And so we can use recursion or self-reference in order to express an unbounded number of elements in our input. So this is how we're going to define lists. So it's just like a linked list. So you all learn about linked lists. They're a self-referential type. So does this look familiar to everyone, this linked list definition? I hope. I think in CS1 or CS2 you probably learned this. So you notice that this type, this struct type, it's self-referential. It refers to its own type. And it's this finite description of what a linked list's type is that allows us to express an arbitrary number of elements in our list. So unlike an array, where we need to allocate a bounded amount of space, you have to call malloc with a fixed amount of space, the linked list data structure allows us to have any number of nodes, up to, I guess, the amount of memory that we have in our machine, but there's nothing limiting in our specification of the linked list to its size, unlike a classic array. And so this self-referential definition is how we're going to handle lists, arbitrarily long data structure or constructs in our grammar. Yeah.
What's the intertype for data void?
This is a C thing. This is how you. It's basically like any. It can be any. It's just a pointer to something. So this is a C thing. I mean, it's basically a container that just contains a pointer to a data. Void star is pointer of any type in C. But yeah, not important for this class. And so we're going to use this self-referential specification in order to express arbitrarily long lists of things in our grammar, and also arbitrarily deeply nested things in our grammar. But let's start with lists. So our specification. So before I showed you what the rules for. Where were they? I showed you the rules for. Oh yeah, okay. Well, I can just go here. I showed you the rules for program and for declaration, but we didn't look at what declaration list was. So remember, a program was a declaration list followed by a function list followed by main, and a declaration list had a finite number of symbols on the right, type, identifier, and semicolon. So how do we support handling any number of declarations in our language? Well, we use this self-referential grammar specification. So let's start with this one. Let's start with this production rule. So remember, the pipe just means there's two different ways to match the declaration list. And so one way to match it is if you see a declaration, which is what we defined here. If you see this declaration in your input, then you must you must see a declaration list afterwards. And so just like the linked list, where we've got some data in our node, and then the linked list node must be followed by another linked list node. We use the same kind of self-referential definition here in our grammar to say a declaration list is always can be a declaration followed by some other declaration list. Questions on this? This kind of makes sense? Yeah. Good question. So there are two production rules here. And so just to avoid making avoid the Bison meta language getting in the way. So there are two productions here. And so you could write this in Bison as well, and it would work just the same. So there are two ways to match declaration lists. We either have this self-referential one, which without any other rules would require infinite input, because it would always, it's like if this were implemented as a recursive function, calling itself, you get a Stack Overflow, you just recurse infinitely. So one way to handle this would be to say, well, a declaration list can also just be one declaration by itself. So we could say that, but then that would mean that every program has to have one declaration. And we may not want that. We may not need one declaration in every program. So there's a kind of conceptual trick in these pattern matching languages that we match the empty string. So this is actually just a comment. And so technically, in Bison, you would just say this. You just literally put no symbols on the right-hand side. And by putting no symbols, you're saying match the empty string. So what this says is, if we see, so for instance, if we see a list of declarations here, we first match, so we know that this is a declaration list because we see a declaration here, followed by a declaration list, and that second declaration list contains a declaration followed by nothing. And the way we match nothing is by having a production like this, where we literally match empty. So yeah, question?
So this is like the same concept of like splitting the statement list into a statement and another statement list.
Exactly. Exactly. So this is exactly what we saw in the toy compiler. Yeah, good point. So in the toy compiler, we use this same construct, and we use null in the linked list for the end of the linked list. For those who have like taken discrete or have seen this grammar, you might have seen epsilon? Who's seen epsilon in like discrete? You've seen, okay, oh, like about more than half of you. So epsilon, what is epsilon in the discrete world?
Empty string.
Empty string, yeah, it's empty string. So again, this is like a meta-language thing. You're using a symbol to represent the absence of text. So this isn't the actual text in the language. This is part of the meta-language for describing the language. It's like the number 0. The number 0 represents nothing. So epsilon means empty string. So so Bison just, there's no epsilon in ASCII. So I put a comment. So this is just a comment so that I don't forget that this is supposed to be empty. So this is just a comment just like in C, or this page intentionally left blank, the IBM kind of joke. But yeah, this is why the meta language of language, this is what makes this so confusing. Because this arrow, this epsilon, these are part of the meta language for defining grammars, not the grammar specification itself. I mean, they're the meta language symbols. So for those of you who've taken discrete, this empty comment is equivalent to saying epsilon. And so conceptually, the parser can recognize there's an infinite amount of empty space between all symbols in the language. So it can recognize empty space whenever it wants, basically. Now, the grammar has to be specified in the right way to actually match unambiguously all inputs, but that's all this means. So we could have said, well, all right, you have to end every declaration with a period, or the word end declaration. So we could have made a token. Let's just say end. So we could have said every declaration must end with the word end, and we could have made a token called end, and then matched declaration lists this way. But language designers just thought it would be easier to just be able to say statement, 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 and not have to put an end symbol at the end of the statement. And so in order to match the fact that you can recognize the end of a declaration list by just the absence of another declaration, we can match an empty set of symbols for a declaration list. Questions on this? This is another one of those kind of mind-bending, recursive, meta things that I think is the fun part of computer science, but also the hard part of computing. Questions? Okay. Lost that head. All right, well, okay, there we go. Okay, so here's what the grammar specification looks like for program, declaration list, and declaration. And so we've got this nested structure that we capture by giving names to our components in our language. And we can express lists with this self-referential grammar specification. Okay, so let me give a quick example of what this list looks like when we actually look at its derivation with a parse tree. So let's say we've got in our input, let's say we've got an input with 3 declarations in it. So when our parser goes to recognize a declaration list, what are the alternatives for a declaration list? What is the right-hand side of the production for a declaration list? Or what are the options for it? Yeah, it's a declaration. There'll be some declaration followed by another declaration list. And so we can capture a record of how the input matches the grammar with this tree. And so on the left-hand side, we have a declaration. And so declaration is type identifier semicolon. And so that'll match this first declaration that we have. But what about this declaration list on the right-hand side? What alternatives do we have to match a declaration list? Yeah.
Either empty or declaration.
Right. So if we just have to match declaration list again, then we can line up the declaration with the actual input we saw, and so on. And so if we keep trying to match the input language with our grammar, we'll end up being able to match all three inputs, all three declarations that we saw in our input, with this tree that records how the grammar matched. But because this last declaration list must have been followed by another declaration list, this is where our empty input comes into play. This is where having that alternative that can also match an empty list allows us to recognize this whole finite input with this recursively defined declaration list structure. Yeah?
And does it not need to contain anything to the left of the last declaration list?
Here? Here?
Yeah. Well,
No, well, at least according to our own specification, we just made one of the alternatives declaration followed by declaration list. The other one was just empty. So this declaration list is matching the other production rule. So there are like two production rules. So this is this is rule 1, and these are all the rule 2 that we had. We had 2 rules for declaration list. Even though they have the same name, there are different ways to match that same construct. And so this is what the parser will do for you. It will recognize that this sequence of tokens here, as long as we recognize the declaration, it'll recognize that it actually does match our input properly. And it does that by figuring out which rules from the grammar to apply to the input in such a way that it will show that our input matches the grammar specification. So how you actually do this is not trivial. It's hard to do this in an efficient way. So in our toy compiler, we had this recursive set of functions that did this recognition. But once you get like empty characters and complex nesting, writing the parser is kind of painful to do, which is why we generated it. It's much better to generate it instead. And so
what's that last declaration?
This one? This is epsilon. So this is for those who haven't done this discrete yet, so this is just empty string. And so kind of theoretically, the conceit here is that there's like an infinite number of empty strings between all tokens, between everywhere in the language. As like a conceit, you can assume that there's any number of empty strings between any symbols in your language. Questions about this? Is this making sense a little bit? So this syntax tree, this is what you'll be producing in your first project. You'll be able to take this ASCII, just plain text file that is just a list of ASCII characters, and your first project will be constructing this tree that represents how this input language satisfies the grammar specification. Yeah?
So are the declaration nodes also pointing to empty string? Or
no, they're pointing to, so I didn't fill out the whole tree here, but this will be a whole subtree that shows how the declaration itself is matched, type, identifier, semicolon. So in our grammar specification, it's either the empty string or declaration followed by declaration list. So it's either of those two rules. And as I tried to record here, some of the applications of declaration list will be one of the rules for the declaration list. So in this case, in this derivation of how we found the parse tree for this input, when there was not an empty string, we knew that rule 2 would have to apply when it's not an empty string. And when there's no other declarations, rule 1 applies when it's an empty string. Yeah?
So does it always check the empty string last then?
So the way the actual parser works doesn't quite work like that. It doesn't actually check for empty. I mean, you can't really check for empty because there'll be a next token to the input. So what ends up happening is that there are other characters afterwards, and if those characters don't match declaration, then the parser effectively infers that it's an empty string that it matches. That's effectively what's going to happen. That's what's going to end up happening. The way we did it in our toy compiler was to look for EOF, right? We looked for a special character. But matching the empty string is not trivial, it's tricky. But basically the parser is going to infer the empty string by deducing that the next input is not part of the construct. That's what's going to end up happening. Questions? So all right, we're getting pretty deep into the kind of meta stuff here in compilers, and I know there's probably a lot to wrap your head around. But once you start doing the project, so in the second half of this lecture, I'm going to show concretely how to actually implement this project. And once you start playing with the trees and seeing what the input and output looks like, how the tree is constructed, I think this will start making more sense to you. All right, questions? All right, let's take a break. Let's come back at 11 sharp, and finish up the second half. All right, everyone. Let's continue with the second half. So the first half we looked a little bit more at grammar specifications, the theory behind them, and how we specify grammars in Bison. So in this part of the class, I'd like to give you the tools and just sort of kick you off with the first project and start actually writing some of these rules that will give us help us generate the parse tree. Okay, so when you clone your Simple C Project 1, so just like before, there's a GitHub Classrooms assignment and a project description, you'll get this grammar file. And it's all written for you already. Here's all the grammar rules. And there's a bunch of to-dos in all of the places where that's where you'll be adding code that will be generating the AST nodes. So let me go over what this grammar format file looks like. So this is documented. If you are interested in reading more about this parser generator, you can also use it to write interpreters. You can use it to do any kind of language processing configuration files. But let me quickly go over how this file is organized. So at the beginning of class, I gave this overview of what Bison looks like. It's got C code at the top for, say, header files or whatever inclusions you want to have. It has their grammar specification, and then C code at the bottom, which is where you'll put functions, say parsing functions or other helper functions. So the syntax is not super like, it's a little archaic. So these percent sign curly braces are used to encode just raw C code that gets spit out into the output. So this tab.c is the actual output code. And so on the right here, we've got the actual output from Bison. And it just literally cuts and pastes this code on the left into the output of the parser. Then we've got the definitions of the tokens in our language. So by convention, we use all caps to denote terminals of the language. And so these are what the Lexer is going to give us. The Lexer is going to give us these whenever, just like in the toy compiler when we said next token, under the hood, Bison is asking the Lexer to give it its next token, and these are the symbols that we use to name each of these terminals in the language, each of the words in the language. So just like in C, we've got identifiers, we have integer constants, string literals, less than operators, greater than operators, keywords like char, int, array, if, else, while, return. And then we'll see in our grammar specification how these terminals are ordered together in order to make the constructs in our language. So C has more tokens than this, but not that much more. I mean, this is all of the words we have in our entire language. It's not that much, right? And so these can all be organized together to make a very large set of possible input programs. This is just saying which symbol is the top of the tree, the starting symbol. These are precedence rules for saying how, say, multiplication and subtraction are, this is order of operations, basically. So this is saying the order of operations of all the symbols in our language. This is more of a parser theory thing. We can talk about this next week or in 2 weeks when we talk about parsing. And so the way our parse tree is going to work is we're going to use this union construct in C in order to specify all of the different types we have in the nodes of our parse tree. So who has seen unions in C before? Not many. Yeah, it's not as common as, say, struct. Who's seen structs? So what does a struct type give you in C? Who'd like to answer? What is a struct type in C? Yeah. Say again, aggregate data type?
Yeah, you can define what types you want to hold inside that struct and continue swapping it.
Yeah, so you can define several fields in the struct, and they'll all be grouped together in memory. And then when you use the struct, you can refer to it by saying like x dot or x arrow, and then the field name. A union works very much the same way, except a struct always has all fields at all times, but a union only picks one of them. The reason we use this for the parse tree in C is we want to have a tree where each node of the tree is basically a different struct, a different type. So we're going to have one struct for statement that points to an expression on the left and a semicolon, or we're not going to have the semicolon, but we're going to have a struct that just points to an expression. And in order to define each of these structs in the same tree, we need to have lots of different data types, one for each kind of tree node we're going to have. So we've got tree nodes for expressions, we've got a tree node for the program. This is all just data type specification stuff. So these are all the possible data types that our nodes are going to have in our tree. And so we basically tell Bison what all the possible return values of our AST construction functions are going to be. But you don't have to worry too much about that. You'll just basically use these constructors. This is a list, this end term, this is a list of all the non-terminals in our language. So above we listed the terminals in our language. Here's the list of all the non-terminal symbols in our language. So program, there's various expressions, there's if statements and while statements, declarations. So these are all the non-terminal symbols fully defined in our language. So not too much, right, for defining this whole C-like language. And this this name in angle brackets here corresponds to the union field. So this is basically effectively how we ascribe types to each of these grammar constructs. So when we see a program, we know it's going to be the prog field in our union. Anyway, you won't have to worry about this too much. I've set this all up for you. But it's just a little bit of the plumbing in order to link the parse tree data structure with the symbols in our grammar specification. That's the bulk of what this stuff is doing here. But at the end of the day, we've got a list of the terminals in our language, and we have a list of the non-terminals in our language. And we have a starting symbol. So if you've taken discrete, you may have learned that a context-free grammar is the starting symbol, all the terminals, all the non-terminals, and all the productions to find a complete grammar. And so after this, there's more esoteric syntax to break up the definitions from the grammar specification. And so here within these, after these double percent sign, this is the grammar rules. These are the rules that map non-terminals to the sequences of symbols. And you can see this looks exactly like what we saw on the slides, where we've got program followed by semicolon, followed by list of symbol names. So notice here that there's also this kind of esoteric thing you saw when you were doing the tool compiler between curly braces. And this is code that gets run after each production is matched. So we'll talk about that more at the end of this lecture, because this is what you're going to be implementing. You're going to be implementing code here. But all this is doing is, this is telling the Bison compiler, this is the code I want you to run whenever you recognize this grammar construct. Okay, questions so far on the Bison file? All right, the main task of this first project is to take our ASCII code and turn it into this tree structure, because that'll allow us to do code generation. And so in order to do that, we need to have some data structure to represent the tree. So I think you've all learned about linked lists. Who implemented trees in C? Did you ever have to implement trees, like binary trees, general trees? Almost everyone, okay. So I think most people had to do tree structures, right? I think you used structs to do that, right? And you said left and right. So this is the same idea, except instead of each node being the same type, being a binary, the struct definition for a binary tree, we have lots of different types of nodes, one corresponding to each construct in our language. So it's very similar to the kind of tree processing algorithms you guys all had to do in CS1, except the tree structure is more complicated. We have more different data types at each node. And the name of this structure that the compiler uses in the front end is called the abstract syntax tree. And so it's abstract because it doesn't contain all the information from the input. The concrete syntax tree, or parse tree, is the tree that contains all the symbols that were given in the input of the program. So for instance, this is the syntax tree because the leaves of the tree contain every single symbol that the input program gave us. The abstract syntax tree removes information that's not needed for compilation. So as I kind of talked way back in lecture 1, abstraction doesn't make sense unless you have a purpose for the abstraction. So why are you using the abstraction? So like a key abstraction. Why do we abstract away all the mechanics of the lock? Well, we just want lock and unlock. We don't care about how it's implemented. So same thing here in the abstraction. We're basing it on what we need for code generation. So there are lots of different uses of the parse tree, for IDEs, for pretty printing, for syntax highlighting. Because we're doing compilation, there are symbols in the input that we don't really care about anymore. So for instance, this semicolon, once we know that we've got a statement, it doesn't really matter that we have the semicolon on the tree. There's nothing in assembly that you translate into from the semicolon. Just knowing that we've got a statement is enough to be able to translate this construct. Same thing with the plus operator. If we've got an addition tree node, then we don't need the plus operator. Or we could design it to have an expression node, and then keep the operator there. So the abstract syntax tree, the goal of this is to just preserve enough information for us to be able to do code generation. So we're going to remove all of the punctuation. We're also going to do some other tricks to improve how the data structures are storing information. So instead of having a tree structure for, say, declaration lists, we're going to turn that into an actual linked list instead of a nested tree. And we're going to be doing data type conversions. So instead of keeping the ASCII symbols for numbers, we'll just convert them during our AST generation. So now, none of this is like some law of nature. These are all design decisions that I made that you have to follow. But these are design decisions I made in the AST just to abstract away stuff we didn't need during code generation. So that way, when you go to write the code generator, you're not digging through fields that just aren't needed for the job. And so as I was pointing out, this AST design, it's just based on need. So, for instance, industrial strength compilers, Clang is a popular front end for C, and it has a mode where it can preserve all the input, so you can do like pretty printing or printing warning messages. It preserves source location information so that you can provide error messages. So it really depends on what you're using it for. So for instance, in the IDE, if you're just doing pretty printing, you may not need to convert ASCII integers into machine integers because you want the text. You don't care about the machine representation of the integers. So this is all just design. So I've tried to make this AST as simple as possible because we're only going to be using it for code generation in this class. But for the question that your colleague asked earlier, what's the difference between is an abstract syntax tree the same as a parse tree, the same as a syntax tree? And so for me, there's really concrete syntax tree and abstract syntax tree. And whenever people say parse tree or syntax tree, that usually implies they mean the concrete one that has all of the symbols in it. But abstract syntax tree is designed based on the need of the compiler. And so for us, that means punctuation's removed, linked lists instead of tree lists, and actual machine integers instead of ASCII code. All right, questions on abstract syntax tree, the meaning of it, or what it does for you, or what it provides? I think I made this a homework question, so you can remember that's the abstract syntax tree. Okay, so as I mentioned, the goal of this first project is to turn raw ASCII code, raw sequences of ASCII characters, into this tree structure. And that captures the constructs in the language that will enable us to do code generation. So Bison, out of the box, if you give it a grammar and you generate a parser for it, all it's going to do is check that the input matches the grammar. It's not going to do anything else. It's just going to read each token one at a time, try to match it to each grammar structure construct you give it, and then you get nothing as the output. You get yes or no, basically. It'll give you a parse error if it doesn't match, or it'll do nothing if it matches. But what we want to use it for is we want to use this process of matching the grammar rules. We want to use this in order to generate an AST for us, a syntax tree for us. So the way we're going to do this is use what Bison calls semantic actions. And the way this works is after each grammar specification for each construct, there's a spot where you can put a little piece of code that will run whenever Bison recognizes that construct. So you can imagine if Bison is going through, just like in our declaration example, Bison's not giving us this tree, but it will tell us whenever it's matched, say, a declaration. And so whenever it matches a declaration, we're going to write code that will create this actual tree node for us. Just like you did in CS1, creating trees. whenever Bison's going to be able to tell us when it matches a declaration, and our code is going to be creating this AST node. To analogize to the toy compiler, you, as you have these recursive parsing functions like parse expression, I gave you also create expression functions. Those are what actually created the data structure. The parsing functions just checked that the input matched the grammar specification. So Bison is going to take over that role for us. It's going to do all the matching. And then we're going to write little snippets of code that create these nodes in our tree. Questions on that? Yeah.
So the additional code, is that the thing that's inside the basis?
Exactly. The curly braces that I showed before, and I'll show this more, and I'll actually do live coding. That's where you put the code. That's Bison's way of allowing you to tell it, here's the code I want you to run whenever you match this input. So yeah, so each rule has one spot at the end of the rule that you can write in curly braces. Here's the code I want you to run, and then yeah, it'll actually run when you go to match it. All right, so let me give an example of what this looks like. Here is our grammar rule for matching what a program looks like in simple C. So just like before, this is the Bison syntax for defining a production. So program symbol decomposes into declaration list, function list, main function. And before the semicolon that ends the rule, in curly braces, this is where you put C code to run whenever you match this rule. And so we can actually look in our generated parser, so parser.tab.c on the right, this is the code that actually gets generated by Bison. If we search for this create program keyword, we can see that it's literally just copied the code into the parser with a few differences. So these special variables here, these money sign prefixed variables, these are not part of C. These are part of the Bison specification language that are basically placeholders. And I think I kind of hinted at this last time, but this placeholder says this is the result of matching this construct. So this is basically where you put the syntax tree node once you've constructed it. So each grammar rule, this double money sign says, this is the value I want to return whenever I match this grammar rule. Just like in the toy compiler, we had when you parse an expression, you would create the expression node and then you return it so that the parent would have access to it. So this double money sign, this is the pattern this is the pattern you're going to use basically on every grammar rule. You're going to create the node and you're going to assign double money sign to that node. And the Bison parser generator is going to be doing all the work in managing where those nodes goes and how they get used to create the tree. Yeah.
Can you just combine the two lines of the program into where C equals create wrong, or?
Oh, so this is just C code. This is just for the main method. This is just for getting the result of the parse. So this is only used once. This is the only place you use it. So I know you probably learned never use globals, but in these kind of old school tools, they depended on globals to do their job. So in the main method, when you call parse doesn't return a value. Actually, you can probably set it up to do that, but the way I set this up is parse doesn't return a value. Instead, it assigns the AST to this program AST variable. And this code is given to you, so you never have to do this yourself. This code is already, this is what the code looks like when you clone your compiler. But this is only for the starting symbol. The starting symbol has the root of the node, and we're just saving the root of the node that we constructed so that when we go to actually print our AST, we have access to the root node. That's all that's for. It's just for saving the root node. The rest of the, you could combine it actually. You could just say program node equals that, but I did this for kind of completeness so that There's probably a way in Bison to just like return it from YY parse. But. So let me look at a different one. So you can get a better sense of what you'll be writing. So the leaves of the tree, they don't have any children under them. They don't have any nested constructs. So all you need to do for leaves of the tree is just call the corresponding AST construction function and then assign it to the return value of matching that construct. So this rule is saying that a primary expression, which is what a construct that I defined for you in Simple C, one of the options for matching a primary expression is to match an integer constant token. And in curly braces, this is us telling Bison, here's the code to run whenever you match an integer token. What I'd like you to do is I'd like you to run this function. This is part of a library of AST construction functions I've given you, so you don't have to manage all the structs yourself. This will create the node and then assign it to the return value for this construct. Yeah?
Can you explain what the $sign is?
Yeah, absolutely. Questions on the double money sign. So if you notice your parse tree is like incomplete or you're getting a segmentation fault, check if you've forgotten to assign the node to the value, to the return value of the construct. Bison calls these semantic values. So the semantic actions assign semantic values. Questions on that? Yeah.
So we need the $2 sign every time.
Every construct will produce some semantic value, some value. In our case, it's the AST nodes, and the way you save that value to the construct that was matched, is use the double money sign to do it. Questions? All right, so we had a good question about what the money sign 1 is. So this is how, so let me go back to the Simple C program. The money sign number variables, these are how we connect parents to children in the AST node. So what Bison will do is when it matches, so in order to match program, we first need to match declaration list. And then we need to match function list. Then we need to match main function, just like the recursive functions in your toy parser. So every time Bison matches one of these grammar constructs, as long as you saved some value, in this case our AST node, you saved it with that double money sign, Bison will make that value available to the parent. So let me show you declaration list. I think I filled this one out. Did I fill this one out? Yeah. So declaration list, this is what declaration list looks like. So declaration list, as we talked about, matches declaration first and then matches declaration list. And so this value, this node that I've created, that Bison created for us when it matched the declaration, this will be made available to program. So program has to match declaration list first. Bison you create a value for that by assigning to double money sign the node for declaration list. That value is made available to use in the semantic action for program. So because we set up declaration list to produce a node, we can use that node by accessing it with money sign 1. So money sign 1 corresponds to the node we produced for the first symbol. Money sign 2 corresponds to the node we produced for the second symbol. Money sign 3 corresponds to the node we produced for the third symbol. Does that answer your question? Does that make sense?
So essentially, like the $1 represents the declaration.
It represents the node, the child node from declaration list. Yeah.
What does that mean for the single $sign numbers in the make declaration list function you showed earlier?
These? So it's the same thing. So money sign 1 corresponds to the, so it's relative to the construct you're in. So money sign 1 corresponds to whatever node was produced by matching declaration. Money sign 2, so it's numbering the symbols in the production. So this is the first symbol, this is the second symbol. And as long as you set this up in this recursive, this composable recursive fashion, whenever the nested construct gets matched, you'll produce an AST node for that nested construct. And that AST node will be made available to the parent construct through money sign 1, money sign 2. Yeah?
Can you say the part about how this relates to child nodes?
Yeah. So, the node, the tree, is like a record of how the parser matched the grammar to the input. And so every time a construct, one of these nested constructs, gets matched, your parser produces an AST node to record the grammar construct that got matched. And the record of that node gets made available to the parent construct for use in creating its node. And so you can think of money sign 1 as containing the child nodes and double money sign as the definition of the current node, the parent node. Does that make sense?
Yeah.
Questions? Yeah.
Can you show that where you create the integer?
Sure. Yeah.
So essentially the integer becomes a declaration child or child.
I mean, what will actually happen when you... I'll show examples. I'll show examples how this gets constructed. So integers aren't used in declarations. They're used in, like, statements. So declarations don't have integers in them, right? They're just type, identifier, and semicolon. But you did raise another point that reminded me of, is that this money sign 1 corresponds to the first symbol here. The lexer gives you values for each of these terminal nodes. So in the same way that you get the child production, the terminal values also will be given through money sign 1, money sign 2. Yeah?
For the identifier, can you explain the argument list before the curly brackets?
For identifier, this?
Yeah, that section before the curly brackets.
This is for function calls. I'll show more of the syntax of this. This is a function call.
Yeah.
We have function parentheses argument list. Questions? Yeah.
So parser.y will create a file called parser.c, right?
Parser.tab.c, yeah.
And then you want us to, or like submitting the assignment, you want us to push the .c file, or you just
No, you just need the parser.y file. Yeah, we'll generate it. We'll generate it. Yeah, you just push the parser.y file. Yeah.
So since an integer is considered a terminal, would the child not like what's the child?
So the child, it'll be the actual symbol in the input program. It'll be like, this is kind of a subtle technical point. So I called these the terminals, but in reality, those terminals have some ASCII symbols that were actually matched. So in the formal world, they call this I think they call this the lexer, and this the token, and this the lexeme. It's like the name of the token versus the actual contents of the token. All this is doing is getting the actual value, the actual symbols, the ASCII symbols from the lexer. That kind of makes sense? So kind of a subtle technical point is that, like, because we have a separate parser and lexer, from the parser's point of view, these are terminals. But they actually do have different, like, it's not just a single symbol. There's actually there's many versions of what an int is. It's any sequence of digits. So this is just a byproduct of separating the parser and the lexer. But it works the same way, where you use money sign 1 to get the the value of this and the value of terminals is their actual ASCII text. But yeah, that's a good question. That's a subtle point. Questions? Okay, let me show an example of what this construction looks like as the parser runs. Yeah, let's use this example again, the declaration tree example. So let's say the Bison parser just recognized a declaration. And we have all of the child, all the child nodes are already produced already for us. We've got type, identifier, and semicolon. So these are already, let's say those nodes are already created. So after declaration is matched, these type identifier semicolon is matched. Sorry. After these three symbols are matched, then Bison is going to run this code for you. So what's going to happen is, after these three things are matched, inside the semantic action, it's going to assign these tree nodes to their corresponding special variable, money sign 1, money sign 2, money sign 3. And our semantic action is then going to call create declaration. So the code that's going to run is create decal, money sign 1, money sign 2, money sign 3. And that's just an AST construction node. It's just creating a struct that can actually, it's abstract, so we don't contain the semicolon. So this is the function that gets run. And the return value of that function is just another AST node. That AST node is going to be some declaration AST node that has these three, I keep forgetting it's the abstract node. It has these two things as children. So that's what create declaration does. Create declaration constructs an actual AST struct and uses whatever Bison provided for the child nodes. Yeah.
So like a post order?
It is, yeah, exactly, yeah. So Bison is called a bottom-up parser. So it is actually constructing, you will be constructing the tree in a post-order fashion. You'll do the children first and then construct the parent. Yeah, that's exactly right. And so what this double money sign does, when you assign this to double money sign, this makes declaration available to whatever its parent is. So I believe declaration is only used as the first symbol. So if Bison determines that you're inside of a declaration list, it's going to assign money sign 1 to this return value. This gets constructed, the double money sign assigns this to the declaration symbol's semantic value. And then it makes that value available to declaration's parent. And this depends on the grammar. In our grammar, declarations are only ever used inside of declaration list. And so this is the recursive behavior. Yeah, exactly. It's a post-order traversal of the tree. And when you say double money sign, it makes that node available to the parent construct. In this case, it'll be the declaration list construct, which will make it available in money sign 1 to the declaration list construct. And this is where that recursive, the self-referential behavior of the parser comes in. Because now the parser has to figure out whether we're matching the first rule or the second rule. So it sees another declaration list. Without knowing exactly how the parser works, let's assume the parser figured out that there was an empty declaration, or there was just some other declaration list over there, and it assigned that to money sign 2. So that may have been empty, it may have been another declaration list, but assuming it figured out already what it was, then it will then run this code. So it'll run create deco list, give it money sign 1, money sign 2, and that will actually create the construct, or the actual data structure construct that holds these two child values, and so on. And then we, make this the return value of declaration list, and it'll be again made available to its parent. So yeah, thinking of this as a tree traversal is the exactly right way to think of it. Except we don't have a tree yet. We just have a recognizer that's going to match grammar constructs and then give you the option to write code that will construct the tree. So in some sense, Bison is doing this post-order traversal of the tree and then giving you a template or a placeholder, a spot for you to run code during that post-order traversal. And so we don't actually have the tree structure yet, but we're constructing the tree bottom up while the parser is recognizing each construct in the input. Yeah?
So for the create deco function example, is there only like another file where the function declarations there and you can see like files of the function?
Exactly, yeah, that's exactly right. So when you actually go to do this process, you'll want to have the specification. You have a couple things open. You want to know the grammar specification for your input language, and you need the AST API, which I've given you, so you don't have to create your own nodes. So I've given you a set of these constructors called create underscore and then some name of the tree structure for each of these. And so, yeah, they're in the project description. Other questions about, I should probably move on to that next to actually explain the project. But yeah, other questions we have here.
So when and where do you use the semicolon? Or like left behind
Yeah, like here. So we didn't use semicolon. So we don't use it. This is our abstract syntax tree. If we've determined that we don't actually need that or I determined for you that you don't need that information for generating code, then it's gone. It's not preserved in the compiler at all. And effectively, what this means is there are some symbols in the language that are really just used for parsing, that are really used to help you identify what construct you have. So, for instance, an if statement. Once you have a node for the if statement and its type is if, you don't need the keyword anymore. So in some sense, some symbols in the language are there to help you disambiguate what construct you have. Same thing with like parentheses. So I think can't remember if we mentioned this last time, but when you're writing math expressions and you use parentheses, what do parentheses mean in writing a math expression? What's that? Precedence. They just change precedence. They don't have any computational meaning, right? Like they don't actually result in some value. They're just symbols that tell you do this first. They tell you how to parse the input. They don't actually have any computational meaning. Same thing with like semicolons and keywords. So yeah, you had a question? Somebody have a question? No, that's not a question. All right, other questions on the beginnings of this? Yeah.
Why did you pass the semicolon to the create declaration? Like I know why you need it to match the rule, but why are you actually passing
Oh, so it isn't being passed. And this is one of the tricky things when you go to write this, is that each one of these, it's you kind of have to parse that each one of these is a separate, you have to look at which symbols there are, and they're base 1. So this is the first symbol, this is the second symbol, this is the third symbol. And that corresponds to money sign 1, money sign 2. This can be especially confusing when you've got symbols. So for instance, let me show you the main function. Okay, so yeah, this is a good case of where trying to line up the numbering is subtle and tricky. So this is the main function, grammar specification, and this is just what I defined the simplicity to be. So everything has a main function. In C, that's not the case because you have separate compilation. But a main function is a main keyword followed by a curly brace, followed by a declaration list, followed by a statement list, followed by the return keyword, followed by expression, followed by semicolon. And so I designed it like this so that return would always be in every function. It makes code generation easier to do that. But so how many symbols are here? How many symbols are in this production? Actually, I missed one. 5, 6, 7, 8. Who says 8? Who says 7 like I accidentally did? Okay, good. You're doing better than me. So yeah, there are 8 symbols here, including these ones in characters. So Bison allows you to just put the raw character in instead of having to pass it through the lexer. So there are 8 symbols here. So which symbol is statement list? Which number is it? Who says 3? Who says 4? All right, good. So it's the 4th symbol. Even though we're not going to be using this, and even though it doesn't have a terminal identifier, this is the 4th symbol. This is the 3rd symbol, and expression is the 6th symbol. So our AST node, in our AST, the way I designed the AST is we don't need the keywords or the punctuation. We just need the nested constructs from the language. And so that's why create main is 3, 4, and 6, because it's corresponding to declaration list, statement list, and expression. And you'll be able to kind of infer which constructs are needed in the AST by looking at the AST API. The types, I hope, should make it clear which grammar construct is expected in the arguments. All right, good questions. Yeah?
Is return like a keyword?
Yeah. Oh, no, it's a keyword in Simple C. So this is one of the terminals in our language. The lexer gives it to us. So the lexer gives us the return. Yeah. The lexer matches the word return and then gives us a keyword. So the only stuff that's Bison here is the colon, these curly braces. These are quoted curly braces. These are ASCII curly braces. These curly braces and the semicolon. And I guess arguably these special variables. So all the other symbols, whenever there's a list of symbols, those are names that we made up to correspond to constructs in our language, constructs or terminals in our language. Questions about this? This is another good example, more complicated example. But here it's really just picking out which of the nested constructs should be part of our tree. And the AST, and yeah, so it may be hard to you don't want to guess that. But the AST API should provide a hint as to what we have in our tree. So the AST, the syntax tree is going to be every symbol. So if we had a syntax tree, every one of these node constructors would have every symbol in it, 1 through 8. The abstract syntax tree is just removing some of those symbols. Like that's, in some sense, that's a large part of all an abstract syntax tree. It's just omitting symbols that you don't need for code generation. You're not going to know yet what and why you need something for code generation, so I've given you the API, which should tell you which constructs are in there. All right, good questions. Other questions? Where's my homepage? Okay, so the assignment is described here and also linked to in web courses. So web courses will Web Courses now has an assignment for Simple C Compiler Project 1. Just like with the toy compiler, it has a link to the project description as well as a link to GitHub Classrooms. So just like with the toy compiler, you'll create your GitHub repository that way. And then here's the description of the project. So the overall goal is to create parser specification file that will generate an abstract syntax tree for our input program. So some directions on accepting the project, how to build your project and run it. These are some descriptions of the AST library. So the nodes are named roughly after the constructs that are supposed to go there. And I'll give a little tutorial on what we talked about today. Some tips about programming. But let me show you the API. So it's a little long. There's one for each. Yeah, there's one for each terminal and non-terminal in the language. I know it's a lot, but they're all the same kind of thing. They're all just tree nodes, and it's just matching the construct. What's that? So for instance, program, it has 3 parameters, decal list, func list, and main, corresponding to declaration list, function list, and main in the grammar construct. So this was our grammar construct for program. So we have these 3 symbols, and we can tell which is the node for it because it bears resemblance to the name of the construct. So it's create prog. And each of the 3 parameters corresponds to the symbols on the right-hand side of the production. And so you can kind of formulaically or systematically, with just sort of good bookkeeping and matching, put the right construct with the right AST construction node. So yeah, I know it looks like a lot, but it's pretty systematic. So once you get through a couple of them and make sure your tree is working, I don't think it'll be too bad. So, for instance, create main. Create main takes a declaration list, a statement list, and a return expression. So looking at our main, you can see that declaration list is the 3rd symbol, statement list is the 4th symbol, and the expression that return takes is the 6th symbol. And if you have any questions, ask on ed discussions, ask in office hours. If you're unsure about which construct is used for which node, yeah.
I had a question about that on ed discussions. If you have questions about the assignment, are we allowed to ask questions?
So if you're in doubt, ed discussions allows you to ask a private question to staff only. So you can use that if you're worried about revealing too much. But if you're not actually putting code or giving answers, it's probably okay. But yeah, if you're in doubt, send a private message. And you can do that on EdStem. And you can send anonymously as well on EdStem. Questions? All right, so here's what it'll look like when you actually create your project. So you'll get this, just like with the toy compiler, you'll get a pre-filled repository. There's a bunch of test files in here, but this is not comprehensive. Please be writing your own test cases. And the only file you have to edit is parser.y. I mean, for submission. You should be making your own test cases. But the only thing you have to edit is parser.y. So this is the one I've been showing you. This is the actual file that you'll be getting in your repository. And so to build it, just like with the toy compiler, you just run make, and if everything builds, you don't have any compiler errors. And to run it, so I've got a simple C program here, a basic one that just does an assignment and a return. I've given you lots of test cases. There's one in the assignment as well, but you should be not relying on our test cases. You should be writing your own test cases for sure. And so once you build it, you get this simple C program, /simple C. And to use it, you pipe in the text of your input program, like so. And what you'll get as output is a tree in this like ASCII art tree structure. Now I'm getting an error because my tree is not complete. So this will make it very clear to you these fatal errors. So the tree printer is checking so you're not going to get a seg fault. It'll check when the tree is incomplete and tell you. So this in-class example, so I've given you enough of the parser to build a tree for this input file. So this is just main return 0, and I think some other things in there as well. But I've given you enough to build a tree for this program. So this is what the tree looks like. Any questions on the tree, like output? Yeah. Yeah, so that's matching the empty production. Yeah, exactly right. So that's basically when there's lists, instead of saying null or something, I put that for completeness so that it would have like the right-hand side. Or it's that version of the deck list. Yeah, that's what empty is. But otherwise, it's kind of like a file tree. You can see that these are the children of Prague, these are the children of Maine. Other questions on the tree structure? Okay, so let me go through filling out the tree for, on this assignment, I've given you a kind of strategy that doesn't just work for writing this compiler, but I think for all programming. This is sort of a test-first kind of programming, although not really the whatever that's called, test-driven or whatever. But it's good to narrow in on what part of the program you're working on first. So what I see a lot of students do, including my own students, is like, somebody gave me a test case, like the teacher, so I'm just going to write the code until that test case works. That seems like a good strategy, but it's actually going to take you more time to do something like that. So it feels faster because it's like, I don't sit there and write a test case and look at the code. I'm just going to get this to work. But I argue that for a large enough piece of code, that's going to take you longer to code. So the kind of delayed gratification, slow and steady, tortoise wins the race kind of approach is to first start with what part of the program you want to implement. That's what I talked about in the first class. You break down the specification first. You don't try to do different pieces of the implementation just to satisfy a test case. Also, just satisfying a test case has no guarantee that you're going to have a working program. And especially in this class, you might have gotten away with it with 100-line programs and like CS1, just bang it out, and there are definitely times hacking is appropriate. But because there are so many different valid inputs to this program, technically an infinite number of possible inputs, trying to teach to the test or trying to build to the test, you're going to have a bad time trying to do that. Because you might get one test work, but then one little change, like I swap the arguments or I have a nested if statement, your input may break. So that's why I think compilers is a really good illustration of this specification-oriented approach, this divide and conquer approach to programming that you can use in all your programming when you want to have reliable and tortoise beats the hare kind of programming. So the first thing to do is pick the construct to implement. Now that's kind of hard, right? Because there's a lot of them. Which one's best? So I would say start with the leaves. Start with the stuff that's closer to the bottom of the tree. And then create the simplest test case that contains that construct. So instead of programming to the test case, create the test cases according to what you're about to program. Now this is much more subtle to do when you've got this complex recursive program than it seems at first. So let me show you why. So here's my input program. I've added, so what construct is this? Can you guess, maybe? So I've added an assignment statement. So I haven't shown you the whole simple C language, but this is an assignment statement. And so here's my assignment statement. It consists of an expression followed by an equal sign, followed by an expression. And now this isn't the lowest part of the tree because there's also an expression node. And that expression node is pretty deeply nested. So I'd like to do something simpler. I'd like to just say do int constant. The problem is, if you notice when I go to run this, that int constant isn't showing up in my tree. Why? Because all the nodes above it, all the constructs above it, haven't been created yet. So the tricky part here is you have a tension here between trying to do all the simple stuff at the bottom of the tree first, but also needing a path to reach that code first. So the easiest way to actually find the path, so let's say I'm doing identifier. To see if your code is reaching that, I just use print statements. There are fancier tools for doing this, but this is the easiest way you can confirm reachability, whether you've actually input, your test case is actually touching the part of the code you're working on. Just this simple act of putting a print statement to test reachability can save you lots of frustration of debugging code that isn't even getting run. So I just use a print statement. So I'd say I want to do identifier. I put a print statement there, and then I need to do something in order to reach that code first. So, what you'll do, you'll sit down and you got to work out the grammar and figure out how that assignment statement reaches identifier. So to make that a little easier, I've given you this whole hierarchy of expressions, part of it already. But you can sit down and trace. Think of it as just a giant recursive program. You're just tracing the path through the whole recursive program. And so if I start filling out this assignment statement, so I'm just going to make sure I can actually reach that. So I've got a parse error here. Okay, so I need a bit more spacing here to make it clear. And so now I've actually reached that here. I can prove to myself that I'm actually touching this code that Bison's generating. So, when you sit down and do this, you'll have to kind of trace these grammar constructs and carefully pick which construct you're going to work on. But once you do that, and once you've proven reachability, the task of implementing will be pretty straightforward. So, so let's implement assignment statement. So we need to find the corresponding AST constructor. So it's this one here. I know you'll have to look through this and get kind of comfortable with the API. I wrote it, so it's easy for me to find it. But here's the construct, assignment statement, and it takes two expressions. So here's my specification on the right here. Here's my semantic action here. So what will the code that I put in here be to create this node, set it to the value so that the parent has it? Yeah? So $$ equals, yeah. So the pattern is $$ equals the AST constructor and then pass in the children to that constructor. So $$ always to set the value for of the current node, and then we call the node constructor, and then there are two children of this assigned statement node, an expression, the left expression and the right expression. So what are we going to populate these arguments with in order to get the child nodes? That, remember, if we've written this correctly, these will be available for us already. We'll already have constructed them in this post-order fashion. So how do we access the left and right expressions of this assignment? Okay, so $1 and who says $2? Who says $3? All right, good. So that's one of the gotchas to look out for. So 1 equal sign is symbol 2, expression is symbol 3. And so the API definition of the AST gives you a hint as to which construct you need in your AST. Okay, so there I'm creating the assignment. Questions on that? I've created that assignment node with the children node. Yeah. I used the wrong what? Oh, yeah, you're right. Thank you. Assign statement. Thank you. I copied it, but I didn't actually use it. Questions on this? And now when I run this, you can see that I've actually reached that identifier construct that I was trying to do before. So this is really just like a giant puzzle that you have to kind of puzzle together all of this reachability, trace through all the recursion, match up the ASG constructors with the grammar node. But it's really just like a giant puzzle. And it's kind of the core of trying to figure out reachability, which is what you need in order to make sure you're testing the code and debugging the code you're testing. So we've reached our identifier here. Let's finish this out by, I probably should have put better spacing. So let's finish this out by actually implementing the identifier semantic action. So what will we have to do here? So what do we always start with? Yeah, the double money sign, $, that's going to be the return value of this, the result. And we're going to need to know which AST constructor to use. So they're usually kind of named similarly. And if you have any questions about this, feel free to ask. I hope it's self-explanatory. So this is the the node constructor, and inside we have string ident expression. So there's really only one symbol here. What's the argument we'll put here? $1. And if you're really curious about what the types are, you can look at the top of the specification file for the types of the nodes. All right. So now let's run this. So we know we've reached that constructor. We know we've reached the statement, and we can look in our tree and confirm that indeed we now have not just main, declaration list, and return. We've also got this statement list node. We've got an assigned statement node, and underneath we have the left and right expressions corresponding to the grammar specification. Yeah.
Is there an image in the lecture now that shows like the tree structure?
For the whole thing? Yeah. So for the whole thing, because there's lots of different ASTs, there isn't just one tree structure. The grammar specification is effectively the schema for all possible syntax trees. So there's nothing really more I can give you. The grammar structure is the embodiment of all possible tree structures. So I guess the tricky part is mapping these. Maybe that's what would be easier, mapping these to the grammar structure names. Would that be more useful to have?
Yeah.
All right. So I'll make a mapping between those things. There's an example here of an input program that has a lot of constructs. But yeah, okay. I'll make a map. Let me make a note for myself to make a map to do this. So map grammar construct names to AST API names, or at least grammar construct names to AST API names, type names. Maybe it's the type names. Okay. Questions? Questions on this? Questions on this task? Yeah.
So you said you start with the test cases and try to have to do that, but you start using the test cases now, right?
Well, so what I mean is, instead of say I'm going to implement this test case, say I'm going to implement this construct, and then pick a test case. I mean, you can use the test cases if it fits, but I think it will be easier for you if you make small test cases for that construct. So I had written one already. That's why I had it. But yeah. And you can use the parser to verify that it's the right, it's valid C. You'll get a parser error if otherwise. The Python will tell you that this is not valid, a valid program. So this will also get you, into writing actual simple C and not just relying on the existing test cases. Yeah. Yes, yeah. So this is matching the grammar construct. So a statement list is a statement followed by an empty statement list. So yeah, those are supposed to be empty. And yeah, it's always a declaration list for every program, but there's no declarations in my actual program. But one of the alternatives for declaration list is just an empty one. All right, so wow, okay, so we're actually a minute over. All right, so that's the first project. So have a good weekend, everyone.